Time travel. Everyone's childhood dream. But is it actually possible in real physics? We're diving into the science, so if you had a time machine, what would you do first? One rule though, no going back to the past with a minigun and causing chaos. Sorry guys, I specifically had to say that out loud. The cleanest scientific definition is simple. Time is what a clock measures. An hourglass counts falling grains, a metronome counts beats, an atomic clock counts tiny, steady vibrations of atoms. A clock doesn't create time. It just counts a regular process to answer one question. How much has passed? In modern physics, time isn't a separate stage from space. Space and time form one structure, space-time. To describe any event, what happened isn't enough. You also need where it happened and when it happened. Our everyday sense that time flows forward is strongly tied to entropy. Disorder is easy to create and hard to undo. Ice melts, smoke spreads out. Mixtures don't neatly unmix themselves. That's why life feels like it has a clear direction, from ordered to more disordered. Intuition says yes, we all share the same now. Relativity says no. What you call now can depend on how you're moving, and this idea that simultaneity isn't universal is the key that unlocks everything weird that comes next. Einstein starts with two simple rules. First, the laws of physics are the same for everyone moving at constant speed. Second, the speed of light in a vacuum is the same for everyone. Together, these two rules break classical intuition and force time to stretch. In relativity, as speed increases, the effects start out subtle but become dramatic near the speed of light. At everyday speeds, the difference is tiny, but as you approach light speed, two things stand out. The moving person's clock runs slower compared to an outside observer, and distances in the direction of motion appear to shrink for that same observer. The Lorentz Factor is simply the tool we use to calculate how large those changes are. The faster you go, the stronger the warping of measurements. A person traveling in a spaceship at a speed close to the speed of light will have their clock run slower, when viewed from Earth, where clocks are at rest. So while 1 year passes for the astronaut, 50 years could pass on Earth, depending on the ship's speed. That's real physics-approved time travel to the future. And it only works one way, only forward. If a spaceship is moving very fast, an outside observer will see its length in the direction of travel as shorter. This is called length contraction. But the truly mind-bending part is this. At the same time is not the same for everyone. Two flashes of light might look simultaneous to someone standing still on Earth, but to someone moving very fast in the spaceship, those same two flashes may not look simultaneous. One can appear to happen before the other, so even now can depend on how you're moving. And that idea is essential for understanding things like the twin paradox correctly. That's not just a philosophical twist, it has real, measurable consequences. The clearest example is the twin paradox. Imagine two twin siblings. One stays on Earth, while the other travels at a speed very close to light, say 99.5% of the speed of light, to a point 25 light years away, and then back. From Earth's perspective, that round trip takes about 50 years, meaning 50 years pass for the twin who stayed behind, enough time to grow older and become a grandpa. But for the twin on the spaceship, time runs slower, so those 50 Earth years amount to only about 5 years on board. They return still looking young. The reason is simple. At extreme speeds, your experience time, proper time, is reduced. And the traveling twin also has to turn around and accelerate. So the situation isn't perfectly symmetric. So yes, physics offers a way to stay young, but there's a tiny catch. Finding a spaceship that can hit 99.5% of light speed is hard. So for now, the most accessible anti-aging plan still looks like Botox, unfortunately. In the twin paradox, speed is what bends time. Now we move to the second pillar of time travel, gravity. Because in Einstein's view, time doesn't change only because of motion, it also changes because of mass. In general relativity, gravity isn't an invisible pulling force. Mass curves space-time like a stretched fabric, and objects simply follow the most natural paths within that curvature. So it's not that something is pulling you, it's that the stage itself, space and time, is being reshaped. And that reshaping makes clocks tick. Different rates pushing the idea of time travel one step closer to something you can actually measure. In stronger gravity, time runs slower, meaning clocks tick a little more slowly the deeper you are in a gravitational field. That's why a clock at sea level doesn't tick at exactly the same rate as one on a mountain peak. Gravity doesn't just pull objects down, it quietly tweaks the flow of time depending on where you are. And yes, just like in the movies, near something insanely massive like a black hole, this effect goes off the charts. So from the outside, it can look like time is almost hitting the pause button. Even if time travel is possible under the laws of known physics, for now it only works in one direction, toward the future. Yes, you could jump forward by traveling close to the speed of light, or by slowing time down through extreme gravity. But the whole go back and grab the lottery numbers idea is still stuck in the foggy, highly debated corner of theory. And honestly, we wouldn't recommend going to the future anyway. Chances are, even if you're the smartest person of your era, you'd land in the future and feel like a Neanderthal trying to become a billionaire on Wall Street. Everything everyone casually knows would sound alien to you, and your mind-blowing knowledge would feel like outdated trivia. So for now, the best strategy is simple. Leave the future jumping to physics, and leave the lottery to luck. If you enjoyed this video, don't forget to subscribe to our channel and hit that like button, and share it with the people you care about, so the light of science can reach everyone.